Welcome. This video, Balloon Payload Program using Amateur Radio and APRS, is presented by the University of Maryland's William KC3 EMR. Assisting William are Steve KD2 DRI, Nick KD2 IFB, and Yahuda KB3 UZY.
We are the Balloon Payload Program, and so what we do is we launch helium sounding balloons into the upper atmosphere. So these are specially designed latex balloons for atmospheric operations. We launch them to a region of the atmosphere that we call the near space, which is above where airplanes fly, but below the traditional altitude for what is considered space. So in these conditions, the temperature is about minus 60 degrees Fahrenheit, and it's somewhere between 70,000 feet and I think the highest balloon altitude was 170,000 feet. So we operate in that range with our altitude balloons. We use helium as a low-density gas because the volume of air that we displace with the helium that we fill in the balloon is lighter than the air that we displace. So we generate lift. Our balloon's about 10 feet in diameter. So when we fill it totally with the helium tanks, we get about 25 pounds of lift. On that, we put 12 pounds of payloads. So a payload is basically, it could be almost anything. But here's a couple of examples. So this is actually, I dug this up in our closets the other day. This is one of the first payloads that we launched. It was from our third launch. We just finished 49.
Wow.
So payloads are essentially little CubeSats, or they don't necessarily be CubeSats, but they do something at this altitude. So they can actuate, they can move mechanical parts. They can fulfill some kind of function, so stabilize something or take pictures, or they can be for communication, which is one of the payloads that I'm going to talk about tonight, and I have some more hardware here too. So we have 12 pounds of these payloads on our balloon. We are limited to 12 pounds by the FAA so that we don't have to file a NOTAM or official notice, even though we do that anyway, just to be nice to the FAA. And we notify everybody so that when we launch, there's no planes in our way, and we're only in the plane altitude for a brief period. So we have 13 pounds of net lift. That means that we get up to our altitude fairly quickly. The reason is because at some points we travel in the jet stream if it happens to be in our area, and during those times, actually our next launch will probably be in the jet stream, our horizontal velocity is about 150 miles an hour.
Wow.
So if we stay in that for a long time, we go way down range, and it makes it much harder for us to get to it. And sometimes there's a possibility, large one, but a possibility that we could end up in the bay or dropping on lovely DC, which would not be very good for us.
Oh.
So we try to attempt not to have that happen. So with the 13 pounds of lift, we shoot up pretty high. Right? We get an average ascent velocity of about 15 feet per second. And we go to somewhere between 70,000 and 110,000 feet. Our highest altitude that we've had in the last couple of years was our most recent launch at 103,000 feet. And I have a picture that we took it down. So when we get there, we fulfill whatever missions it is that our payloads are supposed to do. So Steve and another member of our team, Camden, designed a stabilization payload that can point a payload at in one direction and keep it there throughout the flight using reaction wheel and a couple of servo motors and some other stuff. I have some pictures of that one too. I couldn't bring that one because it's in a lot of pieces, and it's expensive, so we want to keep it at home. So anyway, when we get to our maximum altitude, the pressure decreases as you go up in the atmosphere. I know you guys probably have physics, so I don't need to talk about this. But when we get to our maximum altitude, the pressure decreases when you increase in altitude. And the balloon is slightly pressurized above gauge pressure at mean sea level. So what happens is the balloon, the helium tries to equalize with the pressure outside, expanding the balloon. And when that balloon material can no longer take the stresses, it bursts and releases all the helium, and our balloon falls, basically just free falling for the first 60,000 feet. But we have a parachute already unfurled directly underneath the balloon, so that when it does burst, when it gets to an altitude where the air is dense enough to give some resistance, the parachute inflates, and we theoretically come down nice and gently in the tallest tree in Maryland, of course, because it always happens that way. So, in actual practice, for the first 60,000 feet, we basically just free fall, and then we get to an altitude where the parachute inflates. And it does come down fairly softly most of the time. I have some video that I didn't bring with me, but We know that it comes down pretty softly, so it looks, generally speaking, pretty well. So for tracking systems, we use both UHF and VHF radio systems. So the first one is the one that you guys know the most about, and that's APRS. So we use APRS on our command module. We have primary, secondary, and tertiary APRS trackers. I brought all of them here so you guys can take a look at our hardware, and I will talk about those guys a little bit later. But we use the APRS system, and both ground radios for receiving on the head controller unit, and APRS.FI if we have an internet signal, and these two guys actually do a lot of work with that. So even though we could probably talk about it afterwards, some of the stuff that they do, I'm going to give them props for all the hard work that they've put in fairly recently. So that's for the VHF systems. For UHF systems, we use a 900 megahertz radio. It's a frequency hopping radio between 900 and 928 megahertz. We use that for sending telemetry from the balloon. So it's all of these are omnidirectional antennas until the attitude stabilization system shows that it works. We use omnidirectional antennas, and it broadcasts all of the information that we collect on all of the payloads. So I should mention this first. This payload, the one that broadcasts the 900s, it collects all of our information via very high frequency, or ultra high frequency, 2.4 gigahertz frequency local area network, something called an XP. It collects, oh yeah, we actually have one of those right here. So I'll pass this guy around. The XP unit is right here. It's on top of some of our circuitry. But these little 2.4 gigahertz transceivers transmit all of our data to a central unit, and that transmits it back to us over the 900 megahertz radios. The problem with that is that 900 megahertz are kind of noisy because they're in the ISM band. I'll get to that a little bit later. Then we also use a cellular GSM network transmitter just because when we get below a certain altitude, ground features start to mess with APRS, and the 900s just don't work at all because they're a line-of-sight radio. The cellular network is fairly robust, and it's uniformly distributed, whether in fairly rural territory or in the more urban areas. So we know that we can get a signal on the ground, and we use that for transmitting GPS information that we plot in and go recover our hardware. So I have some pictures here. So this is one of our payloads right here. I designed this one, and I brought it here tonight, so I'm going to brag a little bit. This is called the Looking Glass. And inside we have a spherical camera. So it's a camera that was developed by a Canadian company with, it's kind of interchangeable. We can put different cameras in there, but the one that it was designed for was this. And what it does is it takes 4 tetrahedrally placed cameras and it with wide angle lenses, and it records those images and then laces them together in software so that what you get is an omnidirectional panorama, which is pretty cool. This payload was designed to carry that all the way up to our maximum altitude, record all the data, and then come back down. So what we get is nice pictures of space, which we sometimes have trouble getting different views, different camera views, because we have our balloon string isn't exactly stable as it's going up, and we have all kinds of things. So this was an attempt to kind of get around that. As it turns out, the camera was not very well designed, and the company. So the battery life was only about 15 minutes, which isn't even enough to really get off. So, but this thing works just fine. So what it is it is extruded acrylic that is optical grade, so that it's nice and clear. And then on the ends, it's a 3D printed structure that I designed in CAD to hold everything together and to make the structure airtight. Some little ceilings in there. And then this internal structure is for stabilization. So it keeps the payload.
Condensation and correcting thing?
Actually, none at all. So and even more than that, we traveled through a cloud layer on that particular flight, and we had the highest picture that we got from that payload was directly underneath the cloud layer, and we got no condensation on the inside of that, just because it was totally pressurized, more pressurized than I thought it was going to be. So I didn't want it to be totally pressurized because it will leak pressure when it gets just by natural diffusion. It will leak pressure. But it won't leak it so much when it's coming down because it comes down faster. So what happens is that it's under pressurized on the inside, it's almost a vacuum. And on the outside, atmospheric pressure, so if it hits something, implosion. That's not good for a very expensive camera. That we had on loan. So, yeah. Over here, this is the attitude stabilization payload that I was telling you guys about. So its name is, pardon my language, the Badass. It's an acronym. I don't know what it stands for. He can tell you that.
It's the Balloon Attitude Determination and Stabilization System.
There you go.
Or Badass.
So, we're Badass. Its structure is carbon fiber, and on the inside it has an aluminum reaction wheel that acts like a top, spins at 7,500 RPM, and that stabilizes it in this axis, and then we have some servo motors to stabilize it a little bit further. So the point is that maybe, eventually, we could have a directional antenna, something that we could point at the tracking band and have much higher bandwidth for sending back things like pictures and video and maybe data a little bit more reliably than we do right now. So this is probably the most complicated payload that we've ever designed, and it's still in the process of doing its thing. One of its designers is at Jet Propulsion Laboratory this summer, so he wasn't available to work on. Find the equipment that we use currently to see if there's something better. So we used to use Tiny Tracks APRS tractors, but we found something that was better. It's called a Arduino, which I'm going to talk about a little bit later, but I'm going to pass it around now because it's a big room and I figured people would want to look at it for a little bit. So this is our new APRS tracker. We just finished switching all of our systems over to these guys. It's made by a British company that I have a relationship with because I've talked to them. It's very high quality and it's power efficient. Our Tiny Track system used to be a 12-volt system with a giant battery pack of AA's. So that's weight, and we are restricted in our weight. So anywhere where we can cut that, we need to. These we can power with much smaller lithium polymer cells that weigh a lot less and use a much lower voltage. So I'll pass this guy around just quick. Just want to take a look. The actual APRS module is on the back of this. If you want to try to Google this thing apart, you can, but it's basically the same as this, except it's a little bigger. So,
is that the UHF and VHF transmitters, the two different antennas?
actually, these are both VHF, or well, I don't know. So one is 433 is the 70 centimeter frequency.
Yeah.
It transmits all of our data that we send over APRS, but we haven't really gotten good at using the 70 centimeter frequency yet. It's continuous as opposed to packetized, but we're still working on that part. I figured we would take chunks of things at a time. So APRS.
So this is a dual mode device?
It sends it at the same time, yes. So it sends it at the same time. So they're both sending the exact same data, except one is sending on once every 60 seconds, and one is sending continuously.
Are they both 70 or?
One is 70 and one is 2 meters. So the APRS is 2 meter and the other is a 70 centimeter frequency.
Okay, and what did you call the device?
It's called a Arduino. So it's the people that make it are the people that run the UK High Altitude Society, which are the people that are the most experienced high altitude ballooners that I know of, and they make hardware. So the reason why we switched over to this is because these are people that know our needs very well, because they are way more advanced than us in doing these kinds of operations. So they know all of the problems that we generally encounter with the trackers that we have, and have built hardware specifically designed to defeat all of those problems. So the reason it's called a Arduino is because it's based off something called the Arduino. The Arduino is a little microcontroller board. It has a microprocessor right here, and then all of these little traces, these are the pins for that microcontroller. So it's a really easy way to access the features of a pretty powerful microprocessor and do some very complicated things with a very simple coding interface. So it's the code that you, the programming language that you use is a derivative of the C++ language. It's called Arduino, but it's kind of a weird version of C++.
It basically is C++.
Basically, it's C++.
I could get into more specifics because I'm the programmer.
Yeah, Nick is our programmer.
Yeah.
So when I talk about our AVRS program, you guys can pepper him with questions if you wish. But these things, so we learn these in our engineering programs. We use them for mechanical engineering, at least. I know aerospace does a little bit. We use them for all of our classes to teach people basic programming and hardware actuation skills, because they're not very expensive. They're about $25. And so by doing this, we can continue in that line of the engineering school using these, but at the same time do something very complicated. I'll pass this back around. We've occasionally tried to use something called a Raspberry Pi, which is a more complicated, it's a Linux computer, but they're a little bit more tricky, and most people don't know. You can program in different languages using them. I use Python, I really like that one. But our freshmen don't know how to do that, and we have to be able to transfer our skills fairly easily.
Also,
So, yeah.
heavier, more power.
Oh yeah.
Yeah. All of the above. So then for the third part, one of the major things for research is that we are trying to develop new platforms for people to build on top of. So for freshmen, they have a certain number of things that they can do because we don't have the capability to do other things. So for example, the attitude stabilization payload, that gives us the ability to point something in one direction all the time. So that gives a huge possibility for freshmen to say, okay, well, let's build a direction antenna. Or let's build something that's based on solar. Let's do something that requires me to be pointed in one direction all the time. We have another payload that I'm building right now that's an isothermal chamber that keeps us at the same temperature all the way up to altitude and all the way back down, which is, by the way, very, very hard. So if you have something, if you have the ability to keep something at the same temperature all the time, you can control for certain variables in an experiment and perform a more scientifically valid experiment. So we're always trying to do this for the program, and these tend to be some of our more complicated payloads. They take years to develop. Yes?
Same weight constraint for the constant temperature?
Same weight constraint. All of our launches, we launch in Clear Spring, Maryland, which is just west of Hagerstown. All of our launches are open to the public. It's not uncommon at all for us to have local Hagerstown residents to come by and see what the people with the giant white balloon and the space-looking things are doing.
We have had a couple hammers pick us up and come down and watch.
We have a lot of amateur radio stuff on this thing, and people wonder why. People will come in and say, "Why is there something really noisy in Clear Spring, which is a town with no people?" So we also partner with other teams from other universities, and they bring their own. Some of them bring their own amateur radio hardware. So we have lots of call signs flying on these. I think the most we've ever had on one flight was 6. So we try to use off-the-shelf radio stuff because we are all mechanical or aerospace. And radio is hard, especially designing radio stuff.
Oh, yes.
So we don't have any electricals. We should probably get some. But we try to use hardware that's both proven in the high-altitude community wide as in general, just because when we test this hardware, we don't have a whole lot of launches in a given year to test this stuff. So we can't keep launching it, and we have weight restrictions, so if we keep testing the same broken hardware, it doesn't end up well for us. But if you guys have suggestions, I'm open to it, especially in the radio stuff. We have to have redundancy on all of our systems. So we have 2 Arduinos in the command module. We also have another tracker outside of that, just in case something happens in the command module. For our ground systems, we use, I think, all Kenwoods. They're all Kenwoods.
There we are.
We have 2 700s, and then a 710G and a 710A. 710G we just bought. The reason we bought it is because Nicholas here wrote APRS.FI software, but for offline. So it does the exact same thing, except it's offline, which is something that we really need because we very often do not have an internet signal as we're going through the West Virginia mountains or wherever the hell it is that we are. When we don't have internet signal, we can't use APRS.FI. Now they still record our packets and we can go back and get them later. That doesn't really help us for the actual tracking interface. So we get through the controller unit, we get GPS coordinates. But it's kind of a pain to plot those manually into a computer so that we can route all the vans, especially if we have a big convoy of vans. So FI is really convenient. If we have something that's offline, we don't rely on that, and we can do all kinds of things with our data as we are getting it. So that is Nick, and I wanted to give him a shout out because he wrote that from scratch.
Not quite from scratch.
Almost from scratch. And that is really, really hard. So, and that was just a very recent thing. We only did that on the last launch. So also, we use APRS.FI, as I said. We collect our packet information afterwards, and we post-process, put it in MATLAB, put a map overlay so we can see the profile as it goes up, and see kind of the curve and how quickly it goes up and the profile. And Steve does most of our post-processing stuff with MATLAB, except I get to call you out a little bit because he didn't download our packets from the last launch, which I didn't know about until today. So anyway, we use the 710G because it has a data port on the back where we can option, instead of sending the data to the head controller, so the controller unit, we can send it to the computer, and we can do all of the things that I just mentioned for the offline software that Nick wrote. We can do that instead. It's a newer radio, and we, generally speaking, need new radios every 10 years. But our 700s, I genuinely believe that they're 10 years old, that we've been using them for that long. These things are very long-lived. So when we do the G, we have a 710G in a car as the secondary radio, and then all of our vans have a primary radio, so that the people who are driving the vans, A, have information about what the balloon is doing, like what the altitude is, and B, so that we kind of know how close to the end of the launch we are, because we also have to route the drivers and give them directions, and if they know what the altitude is, they know when that's coming. So it's kind of important for the drivers, having been a couple of times. And when we were first getting started, we had a whole cadre of people leave the program without transmitting their knowledge back to us. And so we kind of had a brain drain. And we started from scratch. And so I contacted Bob Bruniga and said, you are the man who invented this. What would you suggest? And he got back to me in typical Bob style and said, oh yeah, sure, just do this, it'll be fine. And so yeah, we got the 710G, and it's worked out great for us, and I have one in my car now. And so it's great hardware, and I'm sure you guys, yeah.
Your Supersonic Reentry Vehicle there, what is it enclosed in, and is aerodynamics involved in it? Is there a heat involved?
So, yes to all.
Yeah.
So, the original Supersonic was made out of something called APRS foam, which is packing foam. It's made out of insulation foam. Like you've seen the pink foam core they put in insulation for a home. The original one was made out of that for its main structure. When I came on for the Supersonic, we redesigned that. So the inside, it's in two halves. Each of them is about 3/4 of a meter tall, and the entire structure, the entire core structure, is 3D printed at a very low infill, so it's really low density. But the great thing about low density plastic is that it's a great insulator. It contains a lot of air. So it takes a long time for heat to transpire from our electronics to the outside. It has to go through a bunch of layers in between. So the core structure is 3D printed plastic. I should also mention all of our circuitry is custom. So I had some help there with Nick. Nick is now on the Supersonic team with me, and we've both been working on this for a long time. But the outside structure is a combination of two different kinds of foam. One is a spray foam, like what you'd seal a garage with, just to contain or to seal the area between the plastic and the outer foam. And then the outer foam is just a standard EPS packing foam. What we don't know is what kind of heating we're going to get as we drop and try to break the sound barrier. That's something we don't know yet, and we are working on that one. So, yes to that question. And that was good aerospace knowledge. Props.
Ooh.
You may have said this. How long is it? I know that there are some variables, but how long is a typical launch?
Oh, yeah, I haven't mentioned that, and that's great. So typically, when we go to, for our 103,000 foot launch, that was a longer one than usual. But usually it's about an hour and 15 minutes up and about 30 minutes down, just about, something like that. So total flight time is somewhere near about 2 hours. And we launched, like I said, from Clear Spring. During summertime, we come down just west of Frederick for the most part. So it doesn't travel all that far. During the fall, we come down east of Westminster, so very near Baltimore City. So you can see about what the horizontal distance of that is. It's like, what, 150 miles, something like that? It's pretty good ways that this thing travels. And we are following it in van all the way, chasing after it as fast as we can.
We've ended up.
Do you ever have any override systems on your balloons so that they can come down at your will?
So we are somewhat limited in that because the FAA says that we cannot have active control. We try to stay away from that, but it has come up that we want to have the ability to put a valve on it so that we could control where we, not really necessarily for bringing it down, but more for controlling the pressure so that we could float at a specific altitude and have a very long flight. For example, there are some balloons that are launched elsewhere in the world that circumnavigate the world several times. I think 7 was the...
That was the UK people.
People who designed
they circumnavigated
these guys?
the world like 7 times on a single flight. It was the record longest.
Yeah.
One flight, 7 times
One
around?
flight.
They're small, like a party balloon.
So, yeah, they are the the most experienced people I know in that. And they, but I do believe that they use some kind of valve control system for the pressure, because what happens is that you can't control the pressure on the inside of the balloon, so it goes up. But if you have something to control the amount of gas that you have, you can kind of regulate your lift at a certain place and equalize it out. And so what you come out with is basically just a bobber that kind of floats in between the different atmospheric layers. I think I talked about that. So, okay, so I already told you guys most of this stuff about why we use APRS. So mostly it's because when we are coming back, we don't always have line of sight with the balloon. Sometimes we have obstacles in between. Sometimes we just get bad reception. We're in a place where we get lots of reflections and it's just not a good signal. So if we were using the 900 megahertz radios for tracking, that's a direct line of sight system. If you break contact, you lose contact. You don't have any information in between then and when you pick it back up. With a distributed network like APRS, and if they have eye gates in range, we're still uploading all that information to APRS.fi, and we can still get all that information later. And if there's a repeater tower, it's very likely that it's more powerful than our original transmission, and we can get it on the ground, even if we're in a place that doesn't have particularly good reception. So it's also limited access. You have to have a call sign in order to use it. That's one of the major drawbacks for 900s. We get a lot of garbage because it's so noisy. There's so many people using it because it's an ISM frequency, industrial, scientific, medical. You can use that frequency and you don't have to have a call sign. For us, it's still pretty noisy, as was mentioned earlier in the night. It's still pretty noisy around here, but for us, it works perfect. Also, these later two things. I kind of mentioned a little bit of these earlier. We have to have low-cost hardware because we are limited in our budget. NASA's space grant doesn't have infinite money. So we try to keep our equipment as low as possible so that we can fund payloads like the Badass to a much greater degree. So we want to get cheap hardware as much as we can. Also, the same relatively inexpensive hardware has pretty low barriers for entry. We are all students, and we will eventually graduate. Hopefully we'll all eventually graduate. We need to be able to transmit our skills with this and the stuff that we learn onto the next cadre of students, to the freshman students and those that come after them, so that they can run the balloon program and so that we have continuity. If it's a really complicated system and it takes many years to develop skills to use it, we can't transfer those skills and we lose the ability to do things, which is something that we're all trying to avoid pretty actively nowadays. Okay, so these are the call signs that are currently being used on the balloon. We have Steve's and Nick's and mine. The three other people that were certified with us, that passed the test on the same day as all of us with David. Camden Miller, who's out at JPL, who's the other designer of this Badass. Sky Animos, who's one of our French students, but also a resident of Montgomery County. And then Peter White, who's a resident of Montgomery County too, and maybe future members of this amateur radio club. But also, primarily, the university's call sign, W3AX. And so my last couple of slides, I'll skip some of them, but my last couple of slides are about the university's call sign. So the university's call sign is one of the oldest in the United States. The radio club that operates the call sign for the university is one of the oldest in the United States. This is just college. But, so I found some of these from our archive. Our call sign's been in operation since 1932, and our oldest QSO card is from 1933. We have cards from all over the world, from Germany and Japan and everywhere else. And so we've been around for a while. We're one of the oldest in the region, certainly. We received recognition in 1947. And then we are currently, the Ham Radio Club is funded through the Student Government Association. So they are funded through student government at the University of Maryland. Our trustee is here with us, here with Katz. And the president is Perry Block. He wasn't able to make it tonight. But, yeah, so Perry's going to talk about the club a little bit later. So this was the tower that we used for our primary operations for a very long time. I don't know when it was actually put up, but
we moved into that building in 1987.
So sometime after 1987, be it the day after or 10 years after, we have this tower. This was our primary analog repeater station. It's a 60-foot Roan 25G. It seems like it's a common model for a 60-foot tower. And this is a pretty large tower. As you can see, the aerial on top of the tower is almost as long as the tower is tall. And there's a couple of different antennas on there. This is on top of the South Campus dining facility. It is a very tall building with a very tall tower, and it's ideally placed for radio operations, so much so that the FM station for the university is on the same roof, on the other side of it, but on the same roof. So in the past, we've operated our analog station from that repeater station, or from that tower. And because of its ideal location and its height, it not only provided coverage, analog coverage, for the College Park neighborhood, but indeed all of Northeast DC's metro area, because it's such a large tower. We've also been, we've received 2 commendations in the past for assisting local news with the 3 Mile Island crisis and during the U.S. invasion of Grenada. So it plays a public role in public service. This is the tower today. I didn't want to bum everybody out at the end, but this is what our tower looks like today. The story is that some 10 years ago it was struck by lightning and it was damaged, and since then it has fallen into disrepair. The aerial on the top has fallen off completely, and you can kind of see it here lying on the bottom. Some of it's probably salvageable, but most of it is not. There are currently, we kind of zip tied one of the antennas back to the tower last week so that we could attach something to our analog repeater, but until then it had nothing connected to it. So our repeater was on, nothing was attached to it.
There's a tiny piece of coax at the very top. The antenna left about this much on the top of the tower, and that is what our repeater is running on. I mean, you can get it in most of the university, and that's about as far as it reaches.
Yeah, I used to be able to hear it and get into it all the time pretty easily from Petersburg.
These are a couple more pictures of the base, so you can kind of see the state of things right now. So, as I said, it was struck by lightning some 10 years ago, and all of the different funding mechanisms we have for getting this fixed won't work for us. So student government won't allow funding to be spent to repair the tower because, as I understand it, it's because it's a fixed structure?
Yeah, so we can only use student funds to pay for equipment that's movable. And at the same time, they tell us we have to lock it to a desk so no one can take it. But it has to technically be movable. We cannot pay for things like that attach to the building from student money. And that's basically all of our funding right now.
Maryland Space Grant also has the same rule. So NASA Space Grant won't allow us to buy fixed equipment. They won't allow us to spend money that they provide on things like a radio tower. So all of the potential sources that we have for the people that use this equipment most heavily, or would use this equipment most heavily, can't spend the funding that we have on it. So at the very end of this, so anyway, some of the needs that we have for the tower. So it was an analog repeater station. It was not a digifeeder. But there was an urgent need for APRS because we are about to have our 50th launch for the balloon program. It's been, it's 15 years, and I don't, I mean, it's a big deal. We're trying to get as many people as we can to come to it, and we wanted to launch from the university campus. The problem is that we don't have APRS service on our own campus at our own lab because there are no digifeeders anywhere near us, and also because there are a lot of buildings around us. So there is a huge hole in College Park in terms of APRS coverage, which is something that if we're going to launch, we can't lose APRS tracking immediately after we launch our hardware. But more than that, there's also some of these, I think I heard you guys talking about this in your meeting. There's also some of these initiatives that involve radio, like the high frequency hospital net. Things like this are things that we used to be able to participate in as a university that we no longer can because we don't have the range on our repeater. I think the range on our repeater until we fixed it last week was like a few feet, maybe. Now, I don't know, but it's probably not very big. So I mean, it certainly doesn't get out of the university community. But more than that, we have a focus of attention on the tower right now because we have a 50th launch coming up, and it's a big deal for us. It's re-energized and wants to fix the tower, and after so many years, we can finally do this. And for that, we need your help. We have a quote from U.S. Tower Service. They will repair our tower and remove the damaged equipment, but it's $5,000, and that's a lot of money, and we don't have it. As we've mentioned kind of before this thing started, there is knowledge in this room that can A, reduce that cost, and B, maybe find a better solution for all of us. We don't have that knowledge because we don't have the time to develop it in university. You guys do have that knowledge, and we need your help.
Well, that's it for now. We want to thank the University of Maryland's Balloon Payload Program team members. Fantastic guys and a fantastic presentation. And thanks to all of you for your interest in amateur radio.